Afir is an expert on consistency models and distributed systems. In his website jaspen.io, he has some really amazing and great blog posts about distributed systems. In part 1 of today's episode, I want to scan with you one of his greatest blog posts, which is one of the first you should scan while going through his website. The title of the blog post is Consistency Models. Let's begin. In the fundamental concepts section, he says that distributed systems are a type of concurrent system. There is a lot of literature about it, and it applies both to a single node and multiple nodes. There are some differences. However, you can apply the same thing to communication in between processes, which are also a kind of distributed systems. Of course, when you have different computers separate geographically one from another, you have more latency, but you can simulate it all on a single node. Systems have a logical state. In a logical state, it's the state of your system and it changes over time. So we have two concepts as of now. One concept is a state, which we'll discuss. Another concept is time. We are all familiar with time. With state, maybe less. So what is a state? We need to understand these basic concepts in order to get to a more advanced level. What is the state? A state could be a simple integer variable. For example, a state of a variable could be 0, it could be 3, it could be 42. Another term you might have heard is a mutex. A mutex is a special kind of a state. It has only two states. One is called locked, and another one of the states is called unlocked. So, if you are thinking what a mutex is, think two states. Well, simply put, it's like a Boolean, a false or true. So a mutex has two states. One is locked and another is unlocked. Now let's take a look at a simple key value store. In a key value store, we store a map of keys to values. Just think of a standard Java hash map. In a map, you have keys and values. Also in JSON, if you're familiar, you have there also keys and values. So if you have a JSON which one key is a cat and the value is 1, so you have one cat. And maybe you have one dog, so the key is a dog and the value is 1. Or if you had 4 cats, then the key would be cat and the value would be 4. For our case, we just wanted to describe what a state could be. So we said, to review, that a state could be a number, just a number, 0, 3, 42. A state could be if something is locked or unlocked. A state is where a variable is positioned in time, what its value is, or the state of the system. But in our case, in computer and programming, a state refers to a state of a system or a state of a simple variable. So a state of a system can be something very complex, But if you think of a state, it could be simply an integer value, a string value, some value of a variable, or in the case of a system, the state, the position of the system in time. Let's move on to the next concept. The next concept is processes. What is a process? A process is a logically single-threaded program which performs computations and run operations. We say that a process is a singly threaded, but to be more precise, we think of it as a logically single-threaded. It could have in its implementation multiple threads in order to perform its job. It could have even multiple physical nodes. But as long as all these physical nodes or multiple threads are providing us with a cohesive and a coherent single-threaded program, it's an illusion. So when we talk about a process, we talk about an illusion. So a process is not something that was given by the Bible or God. It's it's a term that was created by people, just like a state, just like a system. And a process, just like a state, and just like a system, is something that was created by people, and here we are trying to define it. Multiple people could think of processes and states as different things. Someone can think of a state as the state of the program, something very, very specific. But in our case, when we describe a process, we simply describe something, a program or a machine that does some single cohesive, single-threaded program. Because when we look at a process, we look at it from outside. It's a process. Think about the word process, not to mix it up with computer process. Just in general, the word process, when someone tells you a process, he just means something that is happening. You are not really interested how this thing is happening under the hood. What you are interested is in the process itself. So the same in computers. When you talk about a process, what you are interested at is the coherent, single-threaded program. So we talked about states, we talked about processes and systems, and now let's move on to the next term, which is operations. Operation is correlated to state. When we say an operation, we mean the verb transition, the transitioning from one state to another. It's the cause of this transition. Just think that you have some process and the process is moving in between states, or it has states that are changing their values, and the operation is the transition itself, or the cause of this transition from one state to another. For example, if you have a variable, and this variable can have operations like read and write, then we can get and set the value of these variables respectively. So we can have a counter, and this counter can have operations like increments and decrements, where increment increments the value of this variable by 1. Decrements removes 1 from this variable. So an SQL store might have operations like different operations like select and update, but these are very similar to the increment and decrement. Now let's move on and talk about functions, arguments, and return values. In theory, we could give every state transition a unique name. So a lock has exactly two transitions. One is called lock and another one is called unlock. So we are naming the transitions with unique names. In an integer, we could have many transitions because we could do read the value of 1 or read the value of 2 or write 1 or write 2 or write 3. So we have an infinite amount of different operations that we could do. But in general, we break transitions into functions like general read and a general write, or compare and set, a single operation, or in increment, and specific values with which we can parameterize the functions with. So we could give read the value, the external value which it's reading, or we could give write the value 1 in order to write. So we have a function, a general function. We name this function write. We give it the value of 1 and we expect this function to write the value 1 into the variable. So the state of the variable will change, and when it changes, we name it the operation. The operation is changing the state. It's the cause of the state change. In a transaction store or a database, a value could be a complex transaction. So we could have multiple operations in a single transaction. So the transaction could be read the value of A, then write the value of B, and all this in a single transaction. This is very standard in standard relational databases. Now let's talk about invocation and completion times. Operations take time, right? And in a multiple threaded program, an operation could be simply a function call. In a distributed system, an operation means sending a request from one computer into another. So in a distributed system, you have more latency, where in a single computer, you have less. To model this, let's say that each operation has an invocation time, the time you invoked it. And when it completes, we call this time the completion time. So you ask to read the value of A. When you ask it, when you utter it, this is the invocation time. And when it completes, this is the completion time, and some time passes from the invocation time to the completion time. So, if you have a perfect, synchronized, global, accessible clocks, these clocks could provide us with a real-time order. We could have the actual order of all the invocations and of all the completion times. You would know exactly when each happened, but we do not really have such clocks. And as we do not have such clocks, it's really difficult to track causal ordering of events, such as the invocation time and the completion time. The invocation time is the time you asked for an operation. The completion time is the time the operation has finished. So with this, we finish the first episode. If you are more interested in this, remember either to get back to this, to section 2, or simply go to afirjaspan.io blog and read it. it's really interesting.